Robust fast adaptation in metalearning is a challenging problem, particularly when faced with task distribution shifts. To address this, the authors propose a novel approach inspired by Stackelberg game theory, where task distributions are generated as adversaries to explicitly uncover task structure and increase adaptation robustness in worst-case scenarios. This approach differs from traditional methods, which often rely on implicit task assumptions or heuristics. By generating task distributions as adversaries, the authors can effectively identify and adapt to the most challenging tasks, resulting in improved performance and robustness. The authors conduct extensive experiments to demonstrate the effectiveness of their approach, comparing it to state-of-the-art baselines. The results show significant improvements in performance, particularly when faced with task subpopulation shifts. This is a critical contribution to the field of metalearning, as it provides a robust and adaptive framework for addressing task distribution shifts. The proposed method's ability to generate task distributions as adversaries allows for the identification of vulnerabilities in the adaptation process, enabling the development of more robust models. Furthermore, this approach can be applied to a wide range of metalearning scenarios, making it a valuable tool for researchers and practitioners. The author's findings have significant implications for the development of more reliable and adaptable metalearning models, particularly in real-world applications where task distributions are uncertain or dynamic. By explicitly addressing task distribution shifts, this approach paves the way for more robust and effective metalearning systems. The research paper presents a novel approach to robust fast adaptation under distribution shifts, leveraging the concept of a Stackelberg game. It utilizes normalizing flows to parameterize the distribution adversary for task distribution generation in metal-earner optimization. The solution concept is based on the alternative gradient descent-ascent, with theoretical analysis conducted to understand its implications. The paper outlines a game-theoretical framework designed to handle constrained task distribution shifts and robustify fast adaptation. Key contributions include the translation of robust fast adaptation into a Stackelberg game and the explicit generation of task distributions using normalizing flows. Theoretical analysis and tractable optimization are also emphasized. Experimental results demonstrate that this approach can reveal adaptation-related structures in the task space and achieve robustness improvement in task subpopulation shifts. This work has significant implications for enhancing the adaptability and resilience of machine learning models in real-world scenarios where data distributions are often subject to change. The research paper presents a novel approach to robust fast adaptation in metalearning by introducing an adversarial task distribution generation. This framework is based on a two-player Stackelberg game, where the meta-learner acts as the leader and a distribution adversary as the follower tries to deteriorate the leader's decision. The objective is to minimize the risk function while constraining the distribution shift. The authors propose an optimization problem that balances the risk function with the constraint term, ensuring robustness against task distribution shifts. The paper also presents an example of adversarially task robust MAML, which incorporates the proposed framework into the MAML algorithm. This approach aims to enhance the model's adaptation robustness by capturing the worst-case scenarios in the task space. The proposed framework, adversarial robust meta-learning, consists of two players, the distribution adversary and the meta-player. The distribution adversary aims to transform the initial task distribution to deteriorate the meta-player's fast adaptation performance. The meta-player, on the other hand, attempts to learn robust strategies for fast adaptation in sampled worst-case tasks. The adversarially task robust conditional neural process, ARCNP, is formulated as a minimax problem, where the meta-player seeks to minimize the risk function, and the distribution adversary seeks to maximize the risk function by generating task distributions that challenge the meta-player's adaptation performance. The paper explores strategies for achieving equilibrium in a game-theoretic framework, focusing on robust fast adaptation from adversarial task distribution generation. It proposes using stochastic alternating gradient descent-ascent, GDA, for the meta-player and the distribution adversary to achieve at least a local Stackelberg equilibrium. This approach involves estimating stochastic gradients and reducing variance through baseline adjustments. Theoretical analysis, including convergence guarantees and a generalization bound for meta-learners, is also presented. The evaluation section of the research focuses on the performance of the proposed adversarial training method, ARMAML, in various benchmarks including few-shot synthetic regression, system identification, and meta-reinforcement learning. The goal is to assess the robustness of the model in adapting to task distribution shifts. The experiments utilize task identifiers from Figure 3 to generate diverse tasks. Results show that ARMAML outperforms other methods in the adversarial distribution, while maintaining performance in the initial distribution. The superiority is particularly evident in meta-reinforcement learning benchmarks, such as the point robot and ant-pos navigation tasks. The analysis highlights the effectiveness of the proposed method in improving few-shot adaptation robustness and its ability to discover meaningful task structures. The authors present a comprehensive evaluation of various metalearning algorithms, including MAML, TRMAML, DRMAML, DROMAML, and ARMAML, on several benchmark tasks. These tasks include sinusoid regression, acrobat system identification, and pendulum system identification. The evaluation focuses on the robustness of these algorithms to adversarial task distributions and random perturbations. The results are presented in Table 1, which shows the average mean square errors, MSEs, with standard deviations for each algorithm on each benchmark task. The results indicate that ARMAML outperforms other algorithms in most cases, especially when the initial distribution is uniform. Figures 4 and 5 illustrate the metatesting returns for point robot navigation tasks and ant-pos tasks, respectively. The charts report average and CVAR, conditional value at risk, returns with alpha equals 0.5 in initial and adversarial distributions. The results show that ARMAML achieves higher returns than other algorithms, especially in the adversarial distribution. The authors also evaluate the robustness of the algorithms to multiple tail risk and random perturbations. Figure 6 shows the CVAR values with various confidence levels on the pendulum system identification task, demonstrating that ARMAML is more robust to proportional worst cases across diverse levels. Figure 7 validates the metalearner's robustness on sinusoid regression, where ARMAML's results are more proximal to the y=x line, indicating better performance under distribution shifts. Additionally, the authors test the robustness of the algorithms to random noise from the support dataset. They inject random noise into the support set and evaluate the algorithm's performance on the sinusoid regression task. The results demonstrate the effectiveness of ARMAML in handling adversarial task distributions and random perturbations, making it a robust and reliable choice for metalearning tasks. The performance of ARMAML and DRMAML on clean and noisy tasks is discussed, highlighting their robustness against adversarial distributions. An analysis of the learned distribution adversary visualizes task probability density and its influence by initial task distributions. The impact of shift distribution constraints and compatibility with other metalearning methods are also investigated. Results show ARMAML and DRMAML exhibit lower MSEs than other baselines for all cases, with less severe performance degradation on adversarial distributions. Adversarial training brings more robustness to challenging test scenarios with random noise. The analysis of the learned distribution adversary reveals patterns regardless of initial task distributions, focusing on adaptation difficulties with larger amplitude descriptors. The framework allows for task distribution shifts at a certain level, and empirical tests show increasing the shift constraint alleviates mode collapse. Compatibility with other metalearning methods is explored, with ARCNP showing significant advantages in robustness metrics on adversarial tasks. This paper introduces a groundbreaking method to enhance the resilience of fast adaptation in metalearning algorithms, particularly when dealing with adversarially generated task distributions. The authors propose an algorithm named ARCNP, Adversarially Robust Conditional Neural Processes, which utilizes game theory to model the interaction between the metal-earner and an adversary that generates tasks. The ARCNP algorithm aims to find a Nash equilibrium in this game, representing a balance point where neither the metal-earner nor the adversary can unilaterally improve their performance. This approach is shown to improve adaptation robustness in constrained distribution shifts and facilitates the discovery of interpretable task structures and optimization. The paper also discusses limitations and future work, including the need for accessible task identifiers and the approximate nature of the adopted strategy to derive the game solution, leading to suboptimality in optimization. Future efforts can focus on overcoming these limitations and enabling robust adaptation in various applications. The authors present a comprehensive analysis of the various methodologies and algorithms employed in their research, providing an extensive list of key terms, concepts, and techniques used. They delve into the technical details of their approach, elucidating the rationale behind each method and its significance in the context of the study. The paper begins by outlining the theoretical framework that underpins the research, focusing on the mathematical models and equations that govern the behavior of complex systems. The authors then proceed to describe the algorithms developed to solve these equations, highlighting their novelty and efficiency compared to existing methods. A significant portion of the paper is dedicated to explaining the experimental setup and data analysis procedures, including the statistical techniques utilized to validate the findings. The authors also discuss potential limitations and assumptions inherent in their approach, as well as avenues for future work that could further refine or expand upon the current research. Throughout the text, the authors maintain a high level of technical accuracy and precision, using domain-specific terminology and providing clear explanations of complex concepts. This ensures that the paper remains accessible and informative for expert researchers and stakeholders in the field, while also contributing to the advancement of knowledge in the area of complex systems research. Task-robust meta-learning under distribution shift, a game-theoretic framework. The challenge of task-robust meta-learning under distribution shift constraints is a pressing issue in machine learning. To address this, we propose a game-theoretic framework based on a two-player Stackelberg game. This approach allows for the generation of task distributions that can simulate real-world scenarios more effectively. In this framework, the solution concept involves finding equilibrium strategies for both players. Theoretical analysis shows that this approach can lead to better generalization across different distributions. Experimental results demonstrate the effectiveness of our method using various benchmarks and task structures. We also provide a guideline for implementing our approach, including pseudocode for ARMAML and ARCNP algorithms, and discuss the importance of player order in decision-making. Explicit generative modeling is highlighted as a key benefit of our framework. Our work contributes to the development of more robust and adaptable machine learning models capable of handling distribution shifts. This has significant implications for real-world applications where data distributions are often uncertain or changing. Guidelines for generating task distributions with adversarial training are presented, leveraging normalizing flows to discover task structure under the risk minimization principle. Theoretical foundations are rooted in the Stackelberg game, with supporting analyses. Notably, allowing task distributions to shift within acceptable bounds is a promising area of research in metalearning, with potential to enhance robustness in the face of worst-case scenarios. Pseudocode is provided for implementing adversarial reweight MAML, ARMAML, and adversarial reweight conditional neural processes, ARCNP, in practice. The key distinction between ARMAML and ARCNP lies in the inner loop, where CNP obviates the need for additional gradient updates when evaluating the metal earner. The ARMAML algorithm involves sampling batches of tasks, performing task-specific gradient computations, and updating model parameters. It also incorporates leader-outer gradient descent and follower gradient ascent, with adjustments to the task distribution informed by the Stackelberg game. This approach enables the discovery of complex task structures, fostering improved adaptability in metalearning scenarios. The adversarially task-robust CNP algorithm employs a leader-follower structure for metalearning, enabling fast adaptation. The leader updates parameters via gradient descent, while the follower adjusts the task distribution through gradient ascent. This sequential game involves the distribution adversary and the metal earner, influencing the solution concept. Flow-based generative models facilitate understanding the adversary's behavior and achieving an approximate equilibrium in gradient updates. The setup of base distributions covers a wide range of scenarios, focusing on more challenging cases. Validation is achieved through learned probability task densities and entropies. The authors delve into the related work on robust fast adaptation, an underexplored research issue. They compare their approach with state-of-the-art methods, including MAML, DRMAML, TRMAML, and DROMAML, as depicted in Table 3. The key differences among these methods lie in their task distribution, optimization objectives, and adaptation robustness. The author's approach stands out for its focus on capturing differentiation information from task identifiers, such as masses and lengths in the pendulum system identification, and searching for robust solutions under a distribution shift constraint. This approach is agnostic to metalearning methods and avoids task distribution mode collapse, which might occur in adversarial training without constraints. Two recent strategies for overcoming task distribution shifts are discussed. Group distributionally robust optimization, GDRO, for metalearning, and tail risk minimization, CVAR alpha, for metalearning. GDRO combats distribution shifts via the group of worst case optimization, where the general metatraining objective is written as equation 19. This method enhances fast adaptation robustness by minimizing the worst group risk. Tail risk minimization incorporates the tail risk measured by CVAR alpha in stochastic programming, and the induced metatraining objective is written as equation 20. This approach can be equivalently expressed as an importance-weighted objective, as shown in equation 21, which connects to the group distribution ally robust optimization method. The authors present a novel approach to adversarial generative models, enabling the exact computation of task likelihoods and stochastic gradient estimates. Specifically, the stochastic gradient estimate is derived as equation 22, involving the computation of task likelihoods and a penalty term to prevent divergence from the initial task distribution. Invertible mappings, denoted as G, transform tasks from an initial distribution to a generated distribution, described in equation 23. The paper highlights the theoretical understanding of generating task distributions, involving a distribution shift constraint over the task space. This constraint is formulated as a subpopulation shift under a trust region, where the generated task distribution corresponds to the best response in deteriorating the metalearner's performance under a tolerant level of task distribution shift. The optimization objective, equation 24, involves minimizing the metalearner's loss while maximizing the generated task distribution, subject to a constraint on the distribution shift. This constraint is interpreted as a tolerant region of task distribution shifts, where larger values of delta allow more severe distribution shifts. The authors also provide an equivalent unconstrained version of the optimization objective, equation 25, which includes a penalty term to prevent the generated task distribution from uncontrollably diverging from the initial one. This penalty term encourages the exploration of crucial tasks while avoiding mode collapse. The Lagrange multiplier lambda is configured to be a small value, allowing for a larger scope of shifted task distributions to be covered. Figure 12 illustrates the intuition of distribution shifts and optimization steps. In the presence of a Stackelberg game, optimization involves a delicate interplay between the meta-learner and the distribution adversary. The meta-learner seeks to optimize its parameters to minimize the loss function, while the distribution adversary aims to maximize the loss by perturbing the input data. This dynamic is characterized by a Stackelberg equilibrium, where the meta-learner is the leader and the distribution adversary is the follower. A crucial concept in this framework is the global minimax point, which exists under certain assumptions, including the convexity of the loss function and the compactness of the input space. The global minimax point represents the optimal solution for the meta-learner, which is robust against the worst-case perturbations by the distribution adversary. The convergence guarantee of the optimization algorithm is ensured by the Lipschitz smoothness and compactness of the optimization objective. Specifically, the theorem states that under certain conditions, the algorithm converges linearly to the local Stackelberg equilibrium. The conditions include the boundedness of the input space, the Lipschitz continuity of the loss function, and the step size of the optimization algorithm. The convergence guarantee is critical, as it ensures that the optimization algorithm converges to a stable solution, even in the presence of a strategic distribution adversary. The algorithm's ability to converge to the local Stackelberg equilibrium implies that it can effectively defend against adversarial attacks, making it a robust and reliable optimization method. The authors delve into the learning dynamics of an alternating gradient descent-ascent (GDA) algorithm for adaptively robust metalearning problems. The algorithm iteratively updates model parameters theta and phi using equations 28a and 28b, respectively. The difference between the updated model parameters and the equilibrium point is defined as theta t, phi t, t equals theta t theta, phi t. By leveraging the Lipschitz smoothness of the utility function j, theta, phi, the authors linearize nabla theta j, theta, phi, and nabla phi j, theta, phi, around the stationary point, theta, phi, t, resulting in equations 29a and 29b. They simplify the expression for nabla phi j, theta t plus 1, phi t, in equation 30, using equation 28. This leads to the new form of learning dynamics in equations 31a and 31b, derived by substituting the linearized expressions into the iteration rules. The block terms inside the Hessian matrix H are defined as A, B, and C, with the learning dynamics rewritten in matrix form as equation 32. The authors analyze the expression for the updated parameters norm in equation 33 and provide an upper bound for it in equation 33d, using the Cauchy-Schwarz inequality. They then bound the terms concerning theta and phi separately in equations 34 and 35, respectively, using assumptions and tricks such as the boundness assumption B is less than or equal to L max and the trait of the symmetric matrix P2 is less than or equal to 1 gamma 1 sigma min A. The bounds derived in equations 34c and 35e will be used to analyze the convergence of the algorithm. The optimization strategy's convergence properties are examined, with a focus on the iteration sequence zt, ht equals 0. Property 1 establishes a deduction based on the assumption delta, ensuring the sequence is Cauchy. Property 2 derives that the sequence converges to the local Stackelberg equilibrium with a linear rate. The generalization bound is also explored, particularly the importance weighted generalization bound from 8. This bound is crucial for understanding the generalization in the context of adaptive task distributions. The reweighted generalization bound is detailed, involving the importance variable omega, tau, and the pseudo-dimension c. This analysis is essential for the optimization strategy's performance and understanding its behavior in various scenarios. The authors delve into the supplementary materials of their work in progress, focusing on formal adversarial generalization bounds. They consider the uniform distribution as the base distribution, leading to an equation that involves the logarithmic difference between the likelihood of the task sequence under the true and base distributions. The equation is further simplified using Hadamard's inequality, resulting in a bound that depends on the Lipschitz constant of the invertible functions. This bound is then used to formulate the generalization bound of meta-learners under the learned adversarial task distribution. The authors also present Theorem 2, which states that given certain conditions, including the bi-Lipschitz property of the normalizing flows, the generalization bound can be derived. The theorem involves the pseudo-dimension of the hypothesis space and the logarithmic term, which depends on the Lipschitz constant and the supremum of the loss function. Finally, the authors discuss the benefits of employing normalizing flows in generating task distributions, particularly the tractable likelihood, which enables the analysis of entropy in task distributions. Here is the entropy of the generated task distribution, denoted as p phi asterisk operator, tau, which is derived from the initial task distribution p0, tau, and normalizing flows g equals, gi, mi equals 1. The entropy of the generated task distribution is governed by the change of task identifiers in the probability measure of task space, as shown in equation 45. This is proven by transforming the initial task distribution through normalizing flows, resulting in a derived density function after transformations. The entropy of the generated task distribution is then calculated, yielding equation 46. The experimental setup and implementation details are presented, including the metalearning benchmarks used in the evaluation, summarized in Table 4. These benchmarks consist of task identifiers, corresponding initial ranges, and types of base distributions, comprising sinusoid U, sinusoid N, acrobat U, acrobat N, pendulum U, pendulum N, point robot, and pos ant. The metalearning dataset details are provided, including data preprocessing. The sinusoid regression benchmark is explained, where each task is equivalent to mapping the input to the output of a sine wave, with task identifiers being the amplitude A and phase B. The system identification benchmark is also described, involving the identification of system dynamics in the acrobat and pendulum systems. In this supplementary material, the authors provide additional details on their experimental setup for the metalearning of continuous control tasks. They focus on two dynamical systems, the point robot and the ant from Muhoko, and describe the navigation task where the goal is to guide the robot towards a target goal step by step. The task identifier is the goal location, x1, x2, and the agent performs 20 episodes of exploration to identify the environment and enable inner policy gradient updates as fast adaptation. The authors also discuss their implementation details in PyTorch, particularly the neural modules they developed for their framework, including the distribution adversary and the meta-learner. They rely on the normalizing flow package available for their implementation. Furthermore, the authors present the neural network models for regression experiments with adaptively robust MAML. They introduce the flow module to transform random variables, which is part of the distribution adversary. This module is designed to take a base distribution of task parameters, the dimension of the latent variable, the number of layers in the normalizing flows, the type of normalizing flows, the range of task hyperparameters, and the device, CUDA, or CPU, as inputs. In the normalizing flow (NF) model, the implementation details are crucial for its successful integration with the meta-learner for model-agnostic meta-learning (MAML). The NF model is initialized with either planar or radial flows, depending on the flow type, which sets the stage for the forward pass. This pass involves the calculation of the log determinant of the Jacobian matrix, denoted as logdet, and the subsequent normalization of the data. The logdet calculation is essential for ensuring the invertibility of the flow, thereby maintaining the accuracy of the NF model. The normalization of the data is then performed to obtain a standardized input for the meta-learner. The meta-learner is initialized separately, with its setup tailored for MAML. This setup involves configuring the learner for different tasks, such as sine, acrobat, and pendulum, each with its unique set of hyperparameters. The specific configurations for these tasks are critical, as they directly impact the performance of the meta-learner. For instance, the sine task requires a distinct set of initialization parameters compared to the acrobat or pendulum tasks. The paper highlights the importance of these task-specific configurations in achieving optimal results. The integration of the NF model with the meta-learner enables the leveraging of normalizing flows for meta-learning. This synergy allows for the efficient exploration of complex distributions, which is particularly useful in few-shot learning scenarios. The proposed approach offers a promising solution for tackling challenging meta-learning tasks, paving the way for further research and applications. The implementation details of the distribution adversary and the meta-learner are discussed in this section. It begins with the setup of shared layers, including weights and biases, which are initialized using a uniform distribution. The forward method involves concatenating the input with the task context, followed by linear and ReLU operations. The final layer normalizes task identifiers using min-max normalization. The computation for log probability is also detailed, involving the determinant of the Jacobian of the transformation. This section provides a comprehensive overview of the technical implementation of the model. This research paper presents a novel meta-learning approach that is method-agnostic, focusing on its implementation using model-agnostic meta-learning (MAML) and conditional neural processes (CNP). The authors employ various neural architectures to tackle different benchmarks, including sinusoid regression, system identification, and continuous control. These architectures are specifically designed to handle complex tasks, such as function approximation and control problems. In addition, the authors detailed the implementation of distribution adversaries using normalizing flows, a powerful tool for flexible density estimation. This allows for the generation of diverse and realistic data distributions, enabling the evaluation of tail risk robustness and the impact of shift distribution constraints on model performance. The experiments are conducted using NVIDIA 1080T GPUs and PyTorch as the deep learning toolkit, ensuring high computational efficiency and flexibility. The results provide valuable insights into the efficacy of the proposed metalearning approach in adapting to new tasks and environments, while maintaining robustness to distribution shifts. By exploring the intersection of metalearning, normalizing flows, and neural architectures, this research contributes to the development of more robust and adaptable machine learning models, capable of handling complex real-world problems. In the supplementary materials, we delve into ongoing research on machine learning, focusing on uncertainty quantification and robustness. We explore the performance of different algorithms under various confidence levels and adversarial distributions. For instance, figures 15 and 16 illustrate the CVAR alpha MSS for the sinusoid U and acrobat U benchmarks, respectively. These plots highlight the impact of confidence levels and adversarial scenarios on algorithm performance. Table 5 presents entropy values for initial and adversarial distributions under different lambda values. The data suggests that as the confidence level increases, the MSEs decrease, indicating improved performance. Moreover, the plots in figures 16 and 17 demonstrate the effect of varying Lagrange multipliers lambda on task probability distributions and meta-testing MSEs. This work significantly contributes to the understanding of robustness in machine learning under uncertainty, with implications for future research in this area. In the context of the point robot U benchmark, figure 18 illustrates adversarial task probability distributions and meta-testing mean squared errors, MSEs, with varying values of the Lagrange multiplier, lambda. The first three plots demonstrate the impact of different lambda values on the task probability distributions, highlighting shifts in task probabilities as lambda increases. This is crucial for understanding how changes in the Lagrange multiplier affect the adversarial task distribution and, consequently, the performance of the robot in the benchmark. The last plot in figure 18 shows the meta-testing MSEs across various lambda values. This graph indicates that as lambda increases, the meta-testing MSEs also increase, suggesting a negative correlation between the two. This finding is significant because it implies that higher lambda values may lead to poorer performance in terms of meta-testing MSEs, which could be detrimental to the robot's overall performance in the point robot U benchmark. These results underscore the importance of carefully selecting the appropriate lambda value when optimizing the point robot-U's performance. A thorough analysis of these plots can provide insights into the optimal range of lambda values that balance task probabilities and minimize meta-testing MSEs, ultimately enhancing the robot's efficiency and effectiveness in the benchmark.